Hi, welcome to the next unit. In this unit, which is unit 9, and the next two units, unit 10 and 11, we'll be basically studying compression. Uh, this particular unit is concerned with entropic compression, where the goal is to exploit the distribution and use it to better represent a sequence of symbols from that distribution. Note that this distribution is actually learned as a model or imposed as a model for a given sequence. They may not be an actual distribution which is generating these symbols. So this distribution that we work with, as I had pointed out in the early part of the course, is some model that you've imposed on the observed symbols. So what we will also look at in the next unit is what happens when you learn this distribution from the data itself. Okay, so that paradigm is called universal compression. Both these topics fall under what is called entropic compression, where we want to compress a sequence of symbols to as many bits as the entropy of that source. So, this first lecture, I'll start by looking at variable length source codes. So, we have already introduced the source coding problem. If just to refresh your memory, we had introduced this quantity L epsilon P. Okay, and we were looking at its mathematical features and its mathematical properties, but this quantity L epsilon P can be thought of as the minimum length of, I should not say minimum number of bits required to store a single symbol x from P with some probability of error allowed, with probability of error less than equal to epsilon. So this particular quantity is related to what we can call a fixed length code. Okay, so what is a fixed length code? So fixed length code is where a code we haven't really carefully defined a source code, but a code is of fixed length if each code word is of the same length L. Okay, so in this context, what is a fixed length code? So we can think of two mappings: an encoder mapping E, which looks at this symbol and outputs this sequence L of L bits, which is of the same length for every X, and then a decoder mapping D, which looks at these sequences of length L and outputs a symbol back. So here such a pair E comma D, okay, encoder decoder E comma D is a fixed length code of length L. So that's what a fixed length code of length L is. And what is the probability of error for this code? So the probability of error, PE, let's say, of E comma D, this is the probability of error, is the probability that your output symbol x hat is not equal to x. So this is the same as probability that E of, so the output symbol here is D of E of x, what you stored as a message, this is that part, is not equal to x. That's the probability of error. Okay, so in this language This L epsilon p is the minimum length of a fixed length code. In particular, this L epsilon p will be given by the, so this L epsilon p here will be given by minimum over all L such that we can find a fixed length code of length L and probability of error less than equal to epsilon. Okay, that's what L epsilon p is. And some more terminology. So the different codes that so for different values of x that you see different code different elements here. So look at this set. I'll call it C. E of x as x belongs to x. So for different symbols you have these different sequences of length L. These sequences are called code words. Binary sequences which represent different symbols, and this whole set of code words is called a code. Okay, and it's a fixed length code if each code word has the same length. All right, so we can associate with the code this. We can describe a code in two ways. Either we can associate with it this encoder and decoder mapping, or we can simply provide this list of code words. Okay, so that's what these two representations are not equivalent because you still have to specify which symbol goes to which code word. But we'll sometimes just talk about the code as this set without referring to this mapping. Okay, so we now know what fixed length code is. So what we have been seeing till now, what we have already seen in this course is this quantity L epsilon p, this guy here, is approximately the entropy of p. So we showed two bounds. I'll just recall those two bounds here. We showed that L epsilon p is less than equal to h of p plus square root of variance of minus log px by epsilon. And we also saw that this guy is greater than h of p by 1 minus epsilon. And there was some other correction term here. I think that was yeah, perhaps the correction term here was something like just 1 maybe. Okay, but this is not important. I can't remember it right away. We just applied Fano's inequality. Okay, so L epsilon p was between these two limits. In fact, we later also gave a strong converse style bound where we obtained something slightly sharper. We obtained the lower bound we obtained for L epsilon p was it's more than h of p minus square root variance of minus log px divided by 1 minus epsilon by 2 minus log 2 by 1 minus epsilon. That's the lower bound, and the upper bound that we had was h of p, same one, h of p plus square root variance of minus log px by epsilon. Okay, this was the strong converse, single shot strong converse bound that we obtained. Okay, so these are the bounds. So the upshot of all of this is that this L epsilon p, this quantity that we have studied carefully as a theoretical quantity, we haven't looked at scheme, which we haven't looked at computationally efficient scheme, something that can be used in practice. But this quantity is roughly h of p. Okay, so this one here. Okay, so this L epsilon p is h of p. Okay, So this is something that we have already seen, and the answers were in terms of some sets and so on and so forth. So these fixed length codes are actually quite useful for practice, especially when you have to include your code as a part of a larger protocol. Uh, the other class of codes that we will look at, namely variable length codes, where each symbol can be assigned a binary sequence of different length, they're not so well suited uh, for protocols, because you must assign fixed number of bits for each symbol when you're setting up a protocol. Uh, what in practice, I think the language used is quite different from what we have been seeing in this course. Compression as an engineering field draws a lot from information theory, but it is a field of its own, and there is a different set of language. For instance, something called bit packing is very common in compression literature, and it refers to these fixed length codes at a high level. How do you take these bits? The input symbols are also represented as bits, suppose. Then the question is, how do you take those bits, the input symbol bits, and convert them to this compressed output form, which is also be in form of bits? That thing is called bit packing, and it's nothing but a fixed length source code. Similarly, in a different application, we look at compression for handling, let's say, cache memories and databases, and there the techniques used are very different from what we have been looking at. The techniques used there are closer to the hashing operation that we saw early in the course. So those techniques, we'll revisit them later, I think in unit 11, but they are of different nature. But at the heart of those techniques, they are fixed length codes, but randomized fixed length codes. Here, this mapping E and D are assumed to be deterministic. The encoder and decoder are assumed to be deterministic. But when we do hashes, we can use randomized E and D. If you don't want to do that, you can use something called pseudo-random END, which is used more commonly in practice. So something called a hash like SHA-1, a cryptographic hash like SHA-1, is roughly emulating a random mapping, a random hash. Okay, I'll come to this part later. So the goal here was to point out that the engineering practice of compression is a topic on its own, and these principles that we see in this course lead to those practical engineering answers. Okay, so till now we have only seen fixed length codes. Now, what I want to talk about in this lecture, for the remaining part of this lecture, is this other paradigm of variable length source code. Okay, so a variable length source code also has an encoder mapping E, but this mapping now doesn't produce binary sequence of fixed length. It can produce any binary sequence of finite length. So this is the star is this 0 1 to the power star is the set of all binary sequences of finite length. And the decoder again looks at this binary sequence of finite length and outputs a symbol associated with it. So we can again talk about this pair of mapping ED as the code, and we typically, when we study variable length codes, we don't allow error, although errors can be allowed. So we can define L epsilon p as before, and we'll put a little bar on it to indicate its variable length, and we are looking at average length. So this is a variable length code, and we can talk about its average length, but averaging must be done with respect to the distribution of interest to us. So average length under p. So this guy, the average length of this code under p, is given by summation over x, p of x. This notation, it's the number of bits in this sequence ex. So it's the number of bits used to represent the symbol x. So we represent symbol x using the code word e of x, and this is the number of bits used in that sequence. That's the average length. We can also talk about probability of error as before. Okay, so probability of error for this ED is again, as before, the probability that decoded value of an encoding x is not equal to x. This is the probability of error. Probability of error for ED, the code ED. Okay. So again, these are two parameters of performance: average length, probability of error. For fixed length code, it was fixed length and probability of error. Just like we defined L epsilon p, we can again define now the version for variable length. This L epsilon p bar is, this is the minimum average length over all variable length codes ED with probability of error ED less than equal to epsilon. So minimize this average length over all such codes, this average length over all such codes. Now, one thing to note is that clearly variable length codes include fixed length code as a special case. So this guy here, this quantity here, L bar epsilon p, by definition can be smaller than L epsilon p, because L epsilon p is the minimum that you get by restricting further to fixed length codes, and variable length codes include fixed length codes. So it's smaller than this. But we want to understand how much smaller can it be. Okay, we already saw that h of p is a benchmark for L epsilon p. So our first result, before we look at the practical schemes to achieve L epsilon bar p, our first result is a lower bound, which will set a benchmark for us. So let me state that result. Okay, so I'll write it here. This is a theorem. It says for a discrete distribution P on a finite set X, so this is one part that we assume, and for any epsilon, that the accuracy, the probability of error that we are looking for, between 0 and 1. In fact, we can also allow 0 in this result. Epsilon equal to 0. L bar epsilon p is at least h of p minus some correction term. That correction term is log of h of p. Okay, maybe I'll write the correction term in a different color. Minus log eh of p minus epsilon log cardinality of x minus h of epsilon. Okay, that's the result. So what this result says is that even in this setting, the basic benchmark is the same. A basic benchmark is Shannon entropy. Okay, so that's how you should read this result. The lower bound says that this is more than Shannon entropy, but well, there is a small gain that you can possibly have, but that's just logarithmic in Shannon entropy. So one counting that you should remember for approximation of numbers is the smallest number is log n, then the next smallest number is constant, then the next number is log n, then the next number is linear n, and the next number are polynomials of degree greater than 1, n square, n cube, and then it's exponential, which is very large. Okay, so this one log n is much smaller than this n here. So hp is much larger than log of hp. So this is the leading term in this lower bound. All the other terms are some of the other terms are manifestation of a proof. This, for instance, can be improved. This minus epsilon log cardinality of x. It's just logarithmic dependence on cardinality of x, but you see, this is more than entropy actually. And what you can show is that this can be improved to HP itself. So the real lower bound here is 1 minus epsilon HP. That's the lower bound that you get here. But since I wanted to give a simpler proof, I'm losing this small thing here. Okay. Well, that's the result. So, upshot, L bar epsilon P is still at least HP. Okay. That's the result here. Let's look at the proof of this theorem. So to prove this, we will recall a result that we had seen earlier in the course. So this is one of the properties of entropy for random variables on integers. So what we saw is the following. Property is that, maybe I'll recall it in a different color. Geometric random variable maximizes the entropy, just like uniform maximizes entropy over all random variables with given cardinality of support. So this geometric maximizing random entropy among all random variables with a given expected value. Well, that's the statement in English. Mathematically, what the statement says is, if you have a random variable y, that takes values in integers and has expected value of y equals to some alpha, then what we can show is the following. What the property we had earlier showed that entropy of y is less than equal to alpha log alpha minus alpha minus 1 log alpha minus 1. This is exactly the entropy of a geometric random variable with mean alpha. So that's a result that I want you to remember, alpha log alpha minus 1 log alpha minus 1, and we'll use it in a proof. Okay, so now let's set out to prove this result. L bar epsilon P is greater than HP minus some small correction term. Okay, so to prove this result, let's denote by x hat the estimate of x. So let x hat be, we have to show a lower bound for any encoder decoder. So consider any encoder decoder, any source code E comma D, variable length source code, and denote by x hat the final estimate. So this is the decoded value of the encoded x. Now we know that entropy of P is equal to h of x, but this is less than equal to h of x and x hat. Okay, this is true. And this guy here, h of x and x hat, I will split it into h of x given x hat plus h of x hat. These are actually sort of standard steps that we have seen in the use of Fano's inequality. We basically want to replace entropy of x with the entropy of its estimate. So the first term here by Fano's inequality is less than log cardinality of x plus binary entropy of epsilon plus h of x hat. So we have shown that h of x hat is h of p is less than this guy. Okay. But how do we bring in length here? This x hat is the estimate. How do we bring in this variable length? So to do that, we make an interesting observation. Let's look at this code Cn. So let Cn be e of x. Here n is the variable length. Okay. So here where n denotes the length of ex. So this c superscript n, basically this is a standard notation where we use this notation for the vector c1 to cn. Okay, and what we notice is that this x hat is a function of this c1 to cn. So x hat is a function of this. So what we know for this setting then is that the entropy of x hat must be less than equal to entropy of Cn. Okay, this is true because Cn is a function of x hat. X hat is a function of Cn. Okay, so we take this bound. This is, let's say, equation number 2, and this one here is, let's say, equation number 1, and we combine this 1 and 2. Okay, so by combining this equation 1 and 2, what we get is h of p is less than epsilon log cardinality of x plus binary entropy of this plus h of Cn. Okay, so once again we only have to bound this h of Cn. Okay, this guy here, and you notice that this epsilon log cardinality of x in h plus h epsilon, we actually have retained this as an error term. So we just have to show that h of Cn is bounded above by something. Okay. So h of Cn can be bounded above by h of n comma Cn. Remember, n is also a random variable. It's the length of the random code word. Because x is random, e of x is random, and therefore the length of that code word is also random. So this guy is equal to entropy of n plus entropy of Cn given n. Okay. So remember, so this is a binary vector of length n, this guy here. So given n, this is a binary vector of length n, therefore its entropy is less than equal to log of its length, which is just n, given n, and then there's an expectation over n. So this entropy is less than equal to expected value of n. That's a very important observation. So what we get here is that this whole term here is less than equal to h of n plus expected value of n. Okay, so this is now this is where we would like to use our bound for geometric random variable. So we know that the entropy of this random variable n among all the random variables n with this given expectation en is maximized by the geometric random variable. So we'll denote this by alpha. So notation. Then since geometric random variable maximizes entropy, actually geometric distribution maximizes entropy is a better phrase. The right side, this is the right side, is less than. Okay, so I'm just continuing here. Alpha log alpha minus 1 log alpha minus 1 plus alpha. Of course, this is defined as alpha. Okay, so So that's the bound that we have obtained. Uh, this whole thing is less than alpha log alpha minus 1 log alpha minus 1 plus alpha. Okay. In fact, we can simplify this bound. We can use first order Taylor series approximation of this function x log x here. Okay, so this is some gymnastics. So we look at this function x log x for x between 0 and 1, and we want to bound x log x minus 1 log x minus 1. And the claim I have is first I'll divide by ln2 to convert this base to the base e, and then by first order Taylor series approximation of this function, you can show that this guy is less than equal to ln x for every x greater than 1. Okay, greater than equal to 1. Okay, so this is true. So we can just substitute this bound here. So this guy is less than equal to 1 plus 1 by ln2 plus ln alpha by ln2 plus alpha. Okay. So this is equal to again 1 by ln2 is by the way log e, and ln alpha this is log alpha, and log alpha is log expected value of n. So I just keep it as log alpha plus alpha. Okay, so this is the upper bound for this yellow term here. So what have we obtained finally? All this implies that, so this is the upper bound for this term here. So this guy implies that h of p minus epsilon log cardinality of x minus h of epsilon is less than equal minus this log e is less than equal to log expected value of n plus expected value of n. So we are almost there, except that this bound that we have obtained this bound in terms of we wanted a lower bound for expected value of n, and what we have obtained is sort of an upper bound for this term on the left. Now to prove this part from here on, to proceed from here on, the proof is actually very simple. So suppose HP itself is less than expected value of n, then actually we have a stronger bound. You don't need to prove anything else. Okay, then we have the desired bound. Okay, right. So this is a stronger bound because let's assume that the error term that we had, log e hp plus epsilon log cardinality of x plus h epsilon plus log e, we assume that all this is basically non-negative. Okay, so that's the weakening term. If this guy itself is negative, which can happen when hp is really small, okay, then this is not a good bound. This is only for the case where this guy is non-negative. Okay, then we have a desired bound. But if this otherwise, so if this doesn't hold, this otherwise is for this condition, otherwise, so we have En is less than HP. Okay, so if En is less than HP, what we get is, so we'll just put this part here. We'll get HP minus epsilon log cardinality of X minus H epsilon minus log E, okay, is less than equal to log HP, because En is less than HP, I can substitute here, plus En, expected value of N. And that's the bound we were looking for. Okay, so this is the proof. Okay. So what we have shown is this bound. So we've shown that this bound holds. Actually, to be slightly more careful, what we have shown is L bar epsilon P is either greater than HP, sorry for this, it's either greater than HP or L bar epsilon P is greater than this guy here, whichever is greater, whichever is smaller, HP minus this blah blah blah, this part. Okay, so that's what we have shown. So this is the lower bound. So once again, to conclude, we have obtained, even for this variable length code, the fact that average length is at least HP. And in showing this, we use this interesting idea of we use this interesting fact that geometric distribution maximizes, geometric random variable maximizes the entropy. If you look at a Fano based proof for fixed length code, there also we have used actually the fact that uniform distribution maximizes the entropy for a random variable taking finitely many values. Now, since this random variable can take infinitely many values, we are using not necessarily infinitely many values, but it's taking values in integer. In fact, we could have allowed it to take infinitely many values. This set X need not be finite. A countable set will do. And therefore, we are using a appropriate replacement of uniform distribution, which is this fact that geometric random variable maximizes entropy among all random variables with given expected value. Okay, so that's the result. So we have shown, even for variable length codes, the average length must exceed entropy. Okay, that's what I wanted to show in this lecture. In the next lecture, we will look at some practical codes called prefix-free codes, and we'll state and prove what is called Kraft's inequality. So we are building up towards practical codes, and we know the benchmark we need to attain. We need to find codes with average length close to entropy of P. All right, see you in the next lecture.